Hello, everyone. My name is Peter Oliver. This is The Burning Question. I'm here with Chris Carstens of CarboCulture. Chris, as a member of the founding team and current CTO, tell us about your project.
Well, I am as you said, CTO of CarboCulture, and we are focused on figuring out how to get as much carbon out of the atmosphere as we practically can, because that's really the problem at hand. And so we're working with nature to sequester carbon for geological timescales and do some useful things with that product in the process.
Nice. How do you guys do that?
So it's basically, simplest way to think about it is making charcoal, but the idea here is that nature has done a good job of taking solar energy and CO2 to make sugars that we call carbohydrates. So nature has done that already. The problem is that sugar is edible, and some other organism will eat it, and it'll end up back in the air. So our goal is to make it inert, and we do that by heating it up in a novel pyrolysis process. So we're basically heating it to high temperatures very quickly to keep as much of that carbon as a solid product in the end. So the material comes out looking, I don't know how well the camera will work, but like this is a peach pit that we converted, and looks like a peach pit all the way down to the microscope. You know, you take some in your hand, it's silver gray, electrically conductive, brittle, sounds like glass. So it's neat material, but the most important thing is that, you know, we basically made a mineral out of wood, and this mineral is going to be stable for a very, very long time. Because if you think about like how we date archaeological sites, often is from the charcoal that's there.
Is that right?
That we radiocarbon date. So it's the component that doesn't go away. I saw another thing recently that was they found a like super well preserved dinosaur, like so well preserved up in the tar sands that they could look at its stomach contents, and one of the things they found in its stomach was charcoal. So it was it was eating burnt wood for some reason, like 110 million years ago, and it's still there.
Indigestion.
Yeah. Yeah, exactly. Dino Tums.
Dino Tums. Okay, well, so you said a novel process. So describe how, I think people who are listening to this probably understand a little bit about how pyrolysis works, but tell us how your process is different than, say, you know, a standard, say, torch or even like an open pit fire.
Yeah, well, I've been thinking about this for a long time. Like pyrolysis, charcoal making we've been doing it for a very long time. I joke with people that it's probably the oldest manufactured good that, you know, pre-humans were trading hot coals with each other when the fire went out in one of their caves.
Yeah.
You know, you'd be willing to trade a flint knife for a hot coal to get your fire restarted. But it's interesting that you can do biochar at a very small scale quite easily, like in a kiln or a TLUD, or, you know, making hot coals, and then you put it out with a fire or put it out with some water, right? So get it red hot, put it out. Okay, you've made some. But if you want to do that at a large scale, you start running into problems. And you'd say like peak world charcoal production was probably 1880s, 1890s, when it was used for gunpowder. Like, so
it's interesting. I right around the corner from where we are in the Hudson Valley, there used to be iron smelting factories, and as part of that, they basically chopped down all the forest in the surrounding area and converted them to charcoal to manufacture iron.
Yeah.
So apparently it was an enormous. Apparently all of the railways around here were built for sourcing hardwood for charcoal.
Yeah. So, but the greatest chemistry minds, like in the 1860s, 1870s, were working on charcoal production. What made a good charcoal for gunpowder? It was a critical industry. Like the stuff made from certain wood is different than others. So they were making biochar back then, and it was just kind of a lost art. But to get back to your original question, like
you're not making gunpowder.
No.
If I'm clear.
No, ours is really inert, so it wouldn't make good gunpowder. But if you start trying to scale these systems up, you start running into challenges with heat transfer. Like how do you actually heat the wood evenly, and then you end up with these retorts and continuous augers. And if you don't want any oxygen in there, so because you don't want to burn it up, and so these things start becoming a problem when you start making things, I'd say, like bigger than 2 or 3 feet in diameter. And the other thing is that you end up with is the emissions from it. They're pretty nasty. When you heat something up in an inert atmosphere, it's boiling off different components. So you get methanol and wood vinegar and these things. Again, like at a small scale, that's fine. You can do things with these products, but the liquid component, the tar, some people call it bio oil, and once you actually experience this stuff, and by I mean experience it, get it on your fingers or on your hand, and accidentally rub that hand on your face when you're cleaning something up, and you start feeling it burning. I've never felt anything burn, this black goo that came out. So that starts becoming a real issue at scale. Like, what do you do with it? How do you upgrade it? It's nasty stuff. Then just the smoke and emissions. So you end up where you run into problems with the labor cost. Like if you really analyze where the costs are for biochar, it takes people to move wood around and load it and unload it and et cetera. So, that to an investor that looks bad, or but I mean, if we think about it as a society today, particularly right now, what does that mean? To an investor, it's a cost. To the rest of us, it's a green job.
Right.
And if you wanted to mobilize millions of workers like we did with FDR and the Community Conservation Corps, you would have no problem putting them to work. If we had 10 million people that knew how to use chainsaws and equipment in the forest, it wouldn't be enough to deal with the amount of material we have now. Like, you could multiply the entire forestry industry by tenfold. Like, I don't think people
you just mean out west because there's so much beetle kill and whatnot?
Yeah, it's just and not so much like that climate change is killing stuff that is happening, but also that we have spent 100 years putting fires out, and that just means that fuel is just accumulated decade after decade after decade, and like you end up with drier summer or drier winters. The stuff on the ground doesn't rot, like it needs to be wet, right? When do you see the mushrooms growing? Because they're doing most of the work turning this into back into the atmosphere. But it's like 4% of the Earth's surface that burns naturally every year. So it's a huge. And so when you put that, so you put that out, and now it's just building and building and building and building. So you have areas in the Sierras where you have the standing biomass, like if you just weighed everything on an acre, is 5 or 6 times what it was 250 years ago, like in a natural environment.
Because it was burning much more frequently then.
Yeah, and I was talking to somebody yesterday, Tom Miles, who's the head of the International Biochar Association. He International Biochar Initiative, and he was saying like during the he's up in the Oregon area, and they would do a lot of more prescribed burns, like in the middle part of the 50s, 60s, 70s, like you could do controlled burns. But now, because we have so many people in the urban interface, more people that have gone out into these areas, and because of air quality concerns, et cetera, liability, they aren't doing these controlled burns anymore. So this fuel is just building up, and there's only one way it's really ever going to go away, and that's when it all burns.
Yeah,
and now it's totally out of control. So
because there's so much more biomass above ground that can heat up and consequently extend the temperature or increase the temperature of the fire. Is that
that's a fair assessment. But the critical thing is that it increases the intensity of the fire.
Okay.
So like a natural fire from a lightning strike that happens at a random time of year can smolder and burn through the flames never get over 3 feet tall. It's just kind of burning through the stubble, through the forest floor on its own. And the only thing that's going to put it out is it runs out of fuel or it rains. Like versus when you've loaded it with fuel, loaded it with carbon, all this stored solar energy, like you put a match to it and it just burns very hot, and that heat just bakes, it just sterilizes the soil. And then you kill the microbiome underneath, and then that's when you have real long-term problems, and because you're gonna have to rebuild. It's a moonscape.
Well, so that was fascinating, and let's return to my question. Your machinery does something different than these other things. What does it do?
So we're doing a very controlled combustion under pressure, and I'm not going to describe the real inner workings here. Just suffice to say that we're kind of partially burning the stuff, but very quickly. So having a very fast moving flame front through the material in a controlled way, and so we're basically heating those peach pits up. Or walnut shells or whatever, up to 700-800 degrees Celsius, like in an instant. I mean, so this little peach pit is actually going from a peach pit to carbon in, I actually think it's probably happening in seconds. The question to me is happening in milliseconds, just when that flame gets there. And then it's, because it's heated up so fast, it's turned into it's almost like graphite, and it's electrically conductive, so which is also just cool, right?
It's really cool.
and the other thing is we don't use any external energy, so we aren't heating this up with electricity or using any other energy source. The energy is coming from the material itself, and we're not making any of that nasty bio oil.
Because you're able to get it hotter? Is that you're able to kind of crack we're higher level stuff?
Yeah, so we're able to crack it. So the oils come off, but they are then passed over the hot carbon that's just been made, which is a catalyst for crack. So it just gets turned into either more soot, more carbon when that oil burns. Not burns, but converts, and syngas. So the gas coming off is very rich in hydrogen, carbon monoxide, methane, not very much CO2. So then you can use those gases. They still have embedded energy in them,
right?
And so then those could be a feedstock for doing gas liquids. Really fascinated by some of the like gas fermentation technologies this now. So converting carbon monoxide, but Oh,
Well, I lost you there for a moment, but I got most of that.
Okay.
So in terms of where are you guys in your trajectory? It sounds like you have a machine, but how much can you produce? And we've talked before about using walnut shells. Is that what you guys are currently operating on?
Yeah, so we can make yards a day right now. So it's large enough to show that the technology works. Like that was the purpose of what we built. We need to scale it up further to where we can. So the next step for us is to make something twice as big, and that'll process 4 times as much material, and then we'll show the economics here and get customers for all of that material, sign them up, and right now we're looking at cities for green urban infrastructure, so like bioretention mixes and things like that. And then we'll get that the first Lego brick working properly. The system is modular in the sense that all the pieces of it can be moved around on a flatbed truck. And then we start making first 10 of them, then 100, and then 1,000, and we show that the economics of drawing down CO2 from the atmosphere are even better than fracking. Like that's my dream, because when you fly over the country, when you look down at New Mexico and you see all those drilling pads, like just think of the amount of effort and work that went into that, doing these wells, like drilling holes 3 miles deep, right, and pump 20,000 horsepower pumps, but the economics work, right? And you can make money, and then Goldman Sachs gets in on the game, and you get your lobbyists, and and away you go. But like, you give humans a profitable path, and that's really how you make it scale. Like I don't think it's through incentives or anything else. They can kick that into gear, but like unless you can really make money, it's really hard to do. I've been scratching. It's one of the great frustrations of being around this for 20 years. Is like it's like, do you really expect us to get out of this mess profitably? Like that we're going to drop fossil fuels in $1 trillion industry? Like, oh, forget it. Like, so I digress. All over the place.
Yeah, well, so no, this is fascinating. All right, so I think I would love to chat for just a couple minutes on kind of a most recent project that you mentioned to me, and your work kind of trying to figure out how to use municipal and forest fire waste, and that seems like a really interesting use case for biochar that I haven't heard people talk about much. So can you tell me a little bit more about that?
Yeah, so this is actually happening in Marin County. So this is like where Marin Carbon Project was done, where they showed that you could, like, rangeland application of compost can positively prime the soil. And through the county there, being very progressive, they had set up a drawdown committee. And I don't know what the official tie-in with the drawdown book was, but it's a community activist kind of thing, or community engagement. And I participated in this last year, and we were looking at the problem of what's happening with it. We've had a lot of wildfires here, the one in Santa Rosa in particular, Camp Fire. So the Marin County has passed a tax called Measure C, which is a big deal because it was a self-imposed parcel tax, $20 million a year. And this is a community, 300,000 people are paying for that.
So significant tax, yeah.
Yeah, $20 million. And it was an off-year election, and it got 70% of the vote. Wow. So people recognize that if they don't do something like escape routes, etc., and like if these communities don't take it into their own hands, they can't rely on CAL FIRE to do the work for them. They need to do it themselves. And so they've done some pilot projects. They did $1 million project that cleared a 10-mile evacuation corridor. And it's not a situation like most forests where you can, if you're along a roadside, you can't just put the chips down on the ground, or if it's in somebody's yard. So they ended up with a lot of thousands of yards of wood chips. And
thousands of yards of chipped, just whatever kind of wood.
Yeah, and the way I think about it is like every time you see a chip truck go out, towing a chipper, like where I live in California, the PG&E work, a bucket truck with it's leaving this job site full. Like you can assume that back is filled with something. And so where that carbon, or right now, what they found, what started this whole process is that they did this project, spent $1 million doing clearing, chipping, renting equipment, got workers, all that, and they spent 25% of the money on disposing of the chips. So they spent $250,000 driving 20 miles to the dump.
Is it in California? You have to drop the chips at the dump? I guess you can't
I don't know. Maybe because it was funded through they had to go through official channels. I mean, but this was the mystery, and so it was like that. So we started digging in. Like I see these chip trucks all the time, and I always wonder where did they go? And so we've got this really interesting group of people, including somebody from the Bay Area Air Quality District, UC Berkeley's carbon removal project, some really good consultants, with the idea of doing an analysis of how much stuff is coming out, how much needs to be removed in Marin County, where is it going now, where will it go in the future if there's a bunch more, and then what should we do with it? Because you kind of have three options, right? You can leave it there, it'll decompose, turn into CO2. If you put it in a pile, that's slightly worse because you'll have methane, right? Nature doesn't make piles of chips. not the way it works. So it's kind of unnatural. Very rarely in nature do things heat up and compost. And then, or they truck it off, and then it can go to the land. If it goes to the landfill, up until last year, if you brought that to the landfill was allowed to take those chips, mix it in with the dirt they put over the landfill every day. So they put all the garbage down, and then they have to cover it each night, so to stop odors and stuff. And so they would mix the wood chips in with that dirt. And it makes it so the equipment can drive better. It makes a better layer. It has structural reasons to do this. But what Waste Management was able to do, and I hope I don't piss them off by saying this, is they have to call that diversion. Because they used the wood chips in place of soil, it was technically recycled, and they got to take credit for that as part of the percentage of material that was diverted from the landfill.
Even though they were literally putting it in the landfill.
Yeah.
Okay.
And but they've stopped doing, passed something to kind of stop this. Anyway, it's a dirty business, but what I'm excited about is that there's been lots and lots of studies around what to do with stuff from the beetle kill wood, and in forestry communities, probably because Forest Service, etc. But what's interesting about this Marin scenario, and it's true of so many communities in the West, just like it was this was the hot topic in Australia, right? What material, and so I'm not I joined this committee not to pitch our solution, but I'm sitting on it or trying to steer it towards a comprehensive study or overview of the thing, so we can do a matrix. Like, should you compost it? Should you leave it in place? Should it go onto rangelands? Should you burn it and make energy? Like, let's figure out how to use this asset, because it is interesting. Like, in this discussion, what do you even call this material? Like, people call it woody waste, green waste,
Right?
and it's not. It's an asset. Like, again, nature worked for 50
Really
years
hard.
and did us all a service to grow this stuff, right?
Right.
Like, and we kind of bought ourselves some time by not letting this burn, like letting it accumulate. We're essentially storing carbon, and we can either let it all go up at once in a giant fire, or we can figure out how to use it intelligently. And this mantra, this is you asked me to introduce myself in the beginning. Like, so CarboCulture, the name is like thinking about how do we manage carbon. And our reactor is one technology to do that, but at the end of the day, I think as a society, we need to evolve to be thinking about the carbon footprint of everything we're doing. So, we took one giant leap with agriculture, right? Figuring out something nature was doing, these edible, yummy plants. Oh, let's collect the seeds and let's put them all in one place and control the watering. And, that changed everything. We need to do the same thing with how we manage carbon in the landscape, because it dwarfs what we do. Like, if you can push nature in the right direction or help her out, she can do a lot more heavy lifting than we can.
Yeah.
It's free.
Right. Exactly. It seems like
it's
more
free.
feasible.
It's free, and the only cost is labor. Again, duh. Like,
well, I don't think I can do better than that. Chris, one of the things that I ask everyone before I end the interview is if someone in the community wanted to reach out to you and talk about an area of expertise, what would be your area of expertise that you could say, oh, I would be totally, A, I know a lot about it, but B, I would be totally willing to share what I know. Is there something that sticks out like that?
No, I think it's like this. Anything related to the carbon cycle and how where are the levers to tweak it. Another idea I wanted to throw out to you is we always hear about feedback loops, climate feedback, negative feedback loops, but don't forget that there are positive feedback loops that you can make a change that makes it nature so it draws down more and more carbon, that it will feed on itself. Like, so we just have to nudge it in the right direction, not abuse it. So I love anybody working on this stuff. I'm happy to share what I can.
Okay, thank you so much. And then, is there anyone or anything that you're looking for answers to right now, or kind of questions that you have that you're going, someone else, if you come across someone else in the community that knows about that, you want to hear about it?
Yeah, I mean, I think, for anybody that's watching this for biochar or researchers or people doing that, like, we have a very interesting material that's a lot different, because of how it's made, and interested in these positive feedback loops, or how this material can be used to do other things like filter storm water or clean lead from drinking water. So anybody that is serious about playing with our material and getting their hands dirty, whether it's at home or mixing in their compost, they can honestly look me in the eye and say that they'll actually do something with it. It's not going to end up in a pile somewhere. Then I welcome them to reach out through the website.
All right.
Connect with me on LinkedIn or whatever. But I'm sure.
Yeah, no, I'll make sure if it's all right with you, I'll make sure your contact info is available on the website when we put up the interview.
Awesome. Thank you,
All
Peter.
right. Thank you so much for making time. And
Sure.
and Chris has been an enormous resource for me. So thank you so much for helping me learn so much about this in such a short period of time. So thanks so much.
All right. Cool. Bye.
Take care. Bye.